Finally, let's look at the partition function for translational motion. Again, using our general expression for the partition function as the sum over all states of the probability of a given state occurring, we should be able to substitute the degeneracy of a given state and the energy of any given state into our expression, do the sum, and come up with the partition function for translations. This becomes a little bit tricky though, because the degeneracy of each energy state depends on the energy in a non-analytical way. We cannot write an expression for the degeneracy of each state as a function of the quantum number that describes that state. Remember, however, that the quantum number n is made up of a quantum number for the x direction motion, a quantum number for the motion in the y direction, and a quantum number for the motion in the z direction. And the degeneracy comes from the fact that different combinations of nx, ny, and nz will all lead to the same n squared. So if we simply do a triple sum over each individual nx, ny, and nz quantum number, we will naturally sum over all possible states and all possible combinations, so we can ignore the degeneracy if we do this. In addition, the volume of our box is made up of the product of the dimension in the x direction, A, times the dimension in the y direction, B, times the dimension in the z direction, which equals C. Making these substitutions, we can write our translational partition function as the sum from nx equals 1 to infinity of e to the minus nx squared h squared over 8m a squared times a similar sum for ny and nz. Remembering that nx describes motion in the x direction, ex, the energy in the x direction, which is all kinetic energy, or 1/2 m times the velocity in the x direction squared, is equal to nx squared h squared over 8m a squared. Solving this expression for nx, we can see that nx is equal to 2m a over h times vx, or the velocity in the x direction. Therefore, dnx is equal to 2ma over h dvx. Recall also that translational energy levels are so closely spaced that we can treat them as a continuum. This means we can write each sum as an integral. Thus, the sum over nx becomes an integral of a function of nx dnx. The limits of this integral should be 1 to infinity. However, we will not incur much error by making the lower limit 0. Because nx is related to the velocity in the x direction, we can write this integral using a change of variables in terms of the velocity. So, this should be equal to an integral of a function of the velocity in the x direction, dvx. Because velocity is a vector, and the particles can go either in the positive or negative x direction, the limits should be minus infinity to infinity. However, when nx is equal to 0, vx is equal to 0. So this will give us twice the area of the integral over dnx. So we must multiply by 1/2 to get the proper relationship. Writing the sums over ny and nx in a similar manner, we can now write the translational partition function as qtrans equal to m over h quantity cubed a times b times c times the triple integral, each limit being from minus infinity to infinity, of e to the minus m vx squared plus vy squared plus vz squared divided by 2kbt dvx dvy dvz. The result of this integral is that qtrans is equal to the expression shown here. Notice that we have assumed that the particles have only kinetic energy and no potential energy. This will become important later when we want to include interactions between particles.